Welcome to part 3. I had a small interruption just now, so I stopped that video for that interruption, but I'm going to continue now. So we have a second corollary. So the last corollary basically gave us what we call a certificate for optimality. And what that said was that if you find a dual feasible and a primal feasible solution which have the same objective, then weak duality implies that these are optimal solutions. The second corollary is, I think, a little less obvious, but what it says is that if P is unbounded, then D must be infeasible. How do we prove that? So we use weak duality again. So suppose that P is unbounded, but D were feasible. So we're using what we call a contradiction argument. Then there exists a Y feasible to D. That's what it means to be feasible. You have a feasible point. But then by weak duality, for all X feasible to P, C transpose X is less than or equal to B transpose Y. But P is unbounded. So there exists some X star, say, feasible to P with C transpose X greater than B transpose Y. That's what it means to be unbounded. Any fixed value, you can find a feasible solution with a objective value that's strictly greater than it. This is, of course, a contradiction. You can't have both C transpose X less than or equal to B transpose Y for all X feasible and some feasible X star to P with C transpose X star greater than B transpose Y. Thus, P being unbounded implies D is infeasible. You can prove a similar corollary that shows that if D is unbounded, then P must be infeasible. But note that it doesn't go the other way. And in particular, primal infeasibility does not imply dual unboundedness. It's possible to have both primal and dual LPs infeasible. So if we think about it, you can think about this as a table. Like if you have a primal here and dual here, and you have optimal, infeasible, and unbounded as our three possibilities. And for the dual, up here I'll write O, I, and U. What we just showed is that if P is unbounded, then it means that we are here. And you cannot be here, nor can you be here. And similarly, if you're unbounded in the dual, you cannot be here and you must be here. it's possible for this to occur, them both being feasible. And one question is what about these last three boxes? And we actually have something called strong duality, which I'm not going to prove. I can definitely show you the proof, of course, if you're interested. I'm happy to. It's a bit beyond the scope of our course for me to show you it. But what it basically says is that this is also impossible. And that if you're optimal in one, you're optimal in both. And in particular, if you find if they both have feasible solutions, if they're both feasible, then they both have an optimal solution with the same objective value. This is a very important fact. It has implications in algorithms, implications in modeling, theoretical implications that we use in different proofs in mathematics. It has, you can think of this as a game theoretic foundation, as it provides an alternate, it provides a proof of Nash equilibrium. And that idea is rooted in the idea of X star as being a strategy, a mixed strategy for the primal player, Y star is a mixed strategy for the dual player, and they both have the same payoff. The equal payoff is their objective function. Anyway, there's a lot of theory here that's really important for us. And of course, it's beyond the scope to go too much into it. Right now, I just want you to understand that this is true, and really this table here. What are the possible outcomes in both the primal and the dual? We knew there were three outcomes for any linear program: optimality, infeasibility, or unbounded. Now we know how those outcomes affect us and what is possible in the primal and the dual. In closing, I'm just going to I'm going to just show you a linear program, and you're going to see in this lecture there's a Python file which has Pyomo solving these two linear programs that I have up here. And in that file, what you're going to see is that a couple things. First of all, I want you to note how the way that's written, that the constraints and in the primal are named after the dual variables, and the constraints in the dual are named after the primal variables. That's, of course, intentional. And it's because we should always think about constraints in one being linked to dual variables. I should also note this is a slightly modified version of the linear program that I presented in lesson 22. I modified it so that we would actually have a case where strong duality took place. And as you'll see, if you look at that Python file, an optimal solution that was found was x1 star equal to negative 35.125. x2 star was equal to 13.75. x3 star was equal to 40.375, and x4 was 0. u1 was equal to 0.5. u2 was equal to 6.625, and u3, these are optimal, so we'll call them stars, was equal to 4.5. One thing in their objective, the optimal objective value of both was the same, of course, by strong duality, and that's minus 323.375. Okay, so you can see the strong duality worked here. So this is just an example. Of course, it's not a proof, but it is an example of it. One thing that I want you to note that's particularly interesting is x4 star equal to 0. And consider this constraint here associated with x4. Notice that u1 star plus 8 u3 star is equal to 0.5 plus 8 times 4.5, okay, which is equal to, let's see, 36.5, which is strictly greater than 0. Note in every other constraint in the primal and dual except the x4 greater or equal to 0 except the bounds. So every other constraint in primal and dual except the non-negative bounds, or the bound constraints, the variable bound constraints, are active. So every other constraint except the bounds, not x4 greater or equal to 0, that's active. So x4 greater or equal to 0 is active, but x2 greater or equal to 0, x3 greater or equal to 0, u2, u3 greater or equal to 0, these are the only inactive constraints. They're satisfied, but they're not active. Remember, active is satisfied. So those 1, 2, 3, 4, 5 constraints are the only inactive constraints. Everything else is active. If you plug in the numbers, you're going to see they're all active. That is not a coincidence. It turns out that there's something called complementary slackness. And what it says is that if you have a dual variable, in this case it says, like, for example, if you have minus 4x2 plus 8x4, right, this in this case. And we put stars here. And we multiply it and we subtract the minus 55, the right-hand side. And we multiply it by this u2 star. This will equal 0. If at for optimal solutions. I'm not going to prove that. I don't expect you to know that. But I just want you to notice the pattern. Just start noticing the pattern here. Okay? And that's true. So in other words, the way you might want to think about this is that the pattern of active, if you have an active primal constraint, we should put this, if you have an active, if you have a dual variable that's not 0, that implies that the primal constraint associated with it must be active. Similarly, if you have a primal variable not equal to 0, then that implies that the constraint associated with it must be active. That concludes